Okay, that's a couple of minutes past noon, so we'll commence. Welcome to everyone who's joined us today for an Optimal webinar. Just a little bit of housekeeping. So everyone is currently on mute in attendee mode, which is how the presenters are able to unmute themselves. We will, throughout the presentation, look for an interactive discussion with yourselves ultimately. So through that time, please do feel free to unmute yourselves manually. And also, please utilize the chat option for any questions that you may have. And my colleague Dawn will facilitate the Q&A session. And I will hand over to Rod Mackenzie to begin with the webinar. Thank you.
Thanks, Monica. Welcome, everyone. And today we'd like to discuss with you an insight into RAM modeling and receive your thoughts and feedback on what we're doing. So please sing up. So presenting today is myself, Rod Mackenzie, and Mike Hobbs. Mike, would you like to say a few words about yourself?
Hello, everybody, and thank you again for joining us today. My name's Mike Hobbs. My background is in reliability engineering, maintenance derivation, and simulation modeling. I've been doing this for many, many years in a variety of industry groups across quite a wide range of applications. And I've done this primarily from consulting companies. Thank you.
Thanks, Mike. My name is Rod Mackenzie. I've been involved in oil and gas in Aberdeen now for just over 20 years. Primarily in rotating equipment, gas turbine, overhaul, repair, etc., etc. Last 10 years, I've been in condition-based maintenance and leading into reliability work. So I've joined Optimal back in January, and let's see how we get on from here. Mike, you change the slide, please.
Should be moved on.
There we go. Okay, today's objectives is to provide a little bit of a better understanding of RAM and demonstrate how organizations utilizing early adoption of asset management can smooth out some of the pitfalls throughout the asset life cycle. So I'll give you a brief introduction to Optimal. Mike will give you a RAM overview. We'll discuss where RAM analysis fits in during the different project stages, some of the benefits, the process, share some user cases, and a Q&A. Okay, Optimal Asset Maintenance Solutions was established in 2015 in Aberdeen. Since then, our operations have grown and expanded, with a subsidiary established in South Africa in 2018. Optimal has a team of asset management and reliability experts with the domain knowledge of the full asset life cycle. We are multi-sector experts in the field of asset management with a particular focus on complex enterprise asset data management solutions and reliability engineering. Our research work with the University of Aberdeen, collaboration with Swanee University of Technology in South Africa, and a track record of various asset management optimization projects in the oil and gas, mining and nuclear sectors has focused our understanding of asset management efforts and their maturity. At Optimal, we are passionate about providing bespoke and innovative solutions to enable asset owners to maximize value from their assets based on their specific requirements and operating context. Our values of pioneering and excellence are delivered through our team of dedicated experts which has been proven time and time again through our engagements with our clients and partners. Our partners are a key element of our business model and provide us with access to cutting-edge yet proven technologies. So after that, I'll now hand over to Mike to take you through the discussion. There you go, Mike.
Thank you, Rod. Right. Firstly, we'll just begin with a little bit of an overview just to make sure we're clear really what RAM is. It's a term that we use very often, but we think it would be a good idea just to clarify for the benefit of everybody what we mean by this. So firstly, we mean reliability. This is usually given as a probability. Sometimes it's given as an ability of an item to perform a required function over a given period of time. And as we give that as a 99% perhaps, or a 99.5%, that is the probability you will get to that end time without a failure of a component or an equipment. The availability is the proportion of time an item is functioning over the given time, the life cycle time, or a year or some other calendar time frame, although it could be in other dimensions such as units and so forth. So again, this is going to be primarily quoted as a percentage. Could also be something like a production efficiency, for example. So it can take a number of forms, but it's usually going to be recognized by people as a percentage. Maintainability, there's quite a long description there. And I could probably more easily explain that is that it's simply how easy or not it is to maintain or repair the equipment item. So this might take into account how accessible it is, whether you need special tools that are kept on site or need to be brought in, rigging, scaffolding, all sorts of factors will affect the ability to do a repair or a piece of scheduled maintenance. The significance of this is that that greatly impacts the downtime or the speed at which a failed equipment can be reinstated, and thus there's a direct impact on the availability. We've got a question here. We'd like you to make some notes, please, in the chat box, if you could, as the microphones are muted. So our question for you is, what do you see the benefits of RAM modeling? We're going to be talking about simulation modeling today. So what do you consider to be the benefits from doing that? That's our question to the audience. So where in a project life cycle or the asset life cycle do we see RAM modeling being used? There's a lot of phases throughout the asset life cycle, starting with the early design, the pre-feed, the front end, early front end engineering, procurement, manufacture, construction, installation and commissioning, the operational readiness phases, then the long phase of operations through the operational life, and then eventually into the late life, getting towards the end of production, finishing production, and then decommissioning. And everybody these days has decommissioning as an end of life phase. We do not now just operate and let plant and equipment go. We have to consider the decommissioning phase. There's an awful lot of potential reliability and RAM engineering studies that can be done. Some are more applicable to early phases, some are primarily in the later phases. Today, we're only really speaking about the RAM simulation modeling, the availability simulation modeling, which can occur in early life, is applicable through the operating phase, and is just as applicable in the late life. So how does it all come together? Many of the studies or aspects complement each other. Some will overlap, some will be sitting on their own. Some of the things that we're going to consider in our RAM model are failure rates and their distributions, repair times, logistic delays, spares, resourcing, process dependencies and their relationships is a very key factor. And again, what mitigations are or are not taken when equipment failure occurs. So how do we bring this together? Well, we've got a diagram here which simply shows from one particular package that we sometimes use. We are not reselling software. We're not in the business of selling software packages. We're not a reseller. We're a consulting company. Therefore, we are a user of such tools. So you'll see that the illustrations that I give or the examples that I give will come from a variety of packages. They're not specific to any one modeling program or software application. What are the benefits of RAM analysis? Can I ask, has anybody put anything down? Has anybody entered what they see as the potential benefit for conducting this process?
Yeah, we have a couple. So the first one's from Stephanie Ritchie. Thank you. So
Thank you.
One of the benefits is designing appropriate number of N+1 in project design. And we also have a response from Jodie Lusher, and the cite as a benefit the ability to stimulate different technical and operational models without heavy investment in equipment.
Very good. Thank you. Thank you, both of you. Well, let's see if we've got any of those on our list. So not surprisingly, design configurations is one of the sort of primary uses and primary benefits. Can be done for new plant, new modules that are perhaps being brought in, modifications. So yes, definitely. This is what we call optioneering and different configurations, and N+1 was mentioned. And for example, we might be looking at, I'll give some oil and gas examples as we're in Aberdeen, but it's equally applicable. We could be looking at additional trains of gas compression. We could be looking at, do we do 2 out of 3? Do we do 2 out of 4 generators, 3 out of 4? We can look at all of those different scenarios, and we can consider what the impact is on the availability. It's worth noting that we can do this also in early stages with the sort of pre-feed, just to roughly optioneer different configurations, and we can do it in later stages at a much higher and more higher resolution and detail. The important thing to note when we do it in the early stages is we're looking really at the key changes to the availability, the step changes from the configuration. So we get an idea of how robust the design is. So at the early stages, we wouldn't want to get too fixated on the decimal places. We're looking for the delta changes in things. We might have a requirement and have to confirm that requirement. We might be working to a specification that says you must have a certain availability. We don't know where that number often came from. It may have been built into design, and it has to be proven whether that's possible or not, or that the design actually meets that. And again, if it doesn't, what does the benefit of adding an additional train or a different standby redundant operating regime bring to the design? We can consider many different scenarios, and that might have an impact on safety as well as production from the loss events. We might be considering scenarios from early life through to late life. Late life might have a reduced supply constraint on the supply coming into the process. In the case of oil and gas, particularly with oil, we may have started our life with water treatment facilities that are not suitable for late life, for example, where there's a high degree of water in the oil that's being lifted. And we might want to look at how the failure of that equipment does impact the ability to produce the oil in the late life phase. In the early life, it might not have been so significant, and there would have been other cases around different delivery rates, for example. One that we mentioned just now, maintainability, is a very key area to look into, because we can model in not just the active tool time. So there's logistic delays. Models can be resource or spares constrained. We could also look at regimes adopting fix on fail policies versus scheduled scenarios. So all these different maintenance related elements can be factored into a model. Criticality is another area. Sometimes we may be asked to do a sometimes fairly simplistic model whose primary purpose is just to identify the key areas for more detailed design analysis, maintenance analysis, and so forth. And additionally, we might be simply asked to confirm realistic targets for continuous improvement. It's often the case that targets are set, and these are often not substantiated with modelling or fact. So, for example, somebody may say there's a requirement for this plant to be 99% available. Do we actually know that? Is that realistic? And can we actually prove it? Or has that number been just pulled out of thin air? So there's a whole range of benefits. And thank you for the two contributors. You got two in there. So that's great. Thank you. How do we do this? Well, we touched on earlier that there were a lot of different reliability analyses that can be done at different stages in the life cycle. Just put a few up there. There were many, many there. But today, we're just going to have a look at dynamic simulations. In a modeling package, we would be doing this in a Monte Carlo application. Lots of other methods, but within Monte Carlo, basically what we are doing is repeated random sampling to obtain a numerical results. This is often done in other things such as financial modeling, healthcare modeling, where basically you've got a lot of things that very often you haven't got control over. So you have to model their variance using a statistical distribution. So, for example, we have a life cycle for our equipment, our process, or our plant. We have some downtime. We have an event. The plant has stopped. We have a failure. We need resources. We need spares. We make our repair, and then we carry on for a period of time, and then we get another failure, and then later in life, another failure. So we have an end of life, could be 10 years, 15 years, 20 years or longer. So on the first life cycle, we model those events. Then another life cycle is run, and different events or the same events at different times will occur. This may occur again and again and again, and it's really difficult to do that in any other method than using a software package. So why do we need the software package? Quite simply, it's too many variables for us to consider. Complex, it's too impractical by any other means. We can't take into account all the mitigations. We can't take into account the variability of the data. We can't take into account things that happen if certain other actions happen, but not if something else happens. So there's too many variables. We can't always, in simple applications like spreadsheets, relate to the asset's operation. There could be things like buffer capacity. So for example, where we have a vessel and where we have a pump feeding that vessel, and we have a pump taking the product away from that vessel. If the inlet pump fails, we have a volume in there. If that volume can sustain the process until the first pump is repaired, then we get no impact. However, because we've programmed and put the failures in with failure rates that vary according to the distributions. On some occasions, that pump will take longer to repair, for example, depleting the reservoir, the buffer. And sometimes it won't. That's fine. But now the buffer is empty, and does another failure occur before the buffer has filled again? So even that alone can get quite complicated. We've also mentioned different maintenance strategies and resource limitations. But for oil and gas, it could be things such as reservoir profile, tanker offtakes for FPSO storage vessels, flaring constraints, buffering again through the volume within the reservoir or through where the product is going, the pipeline capacity, for example. So there's all sorts of things, could be weather related, for example, as well. So there's a whole variety of things that in increasing levels of detail we can decide if we wish to put into a model, and we can't do that unless we're using some sort of modeling package. So in summary, really, it's easier to investigate the impact of uncertainties and focus on the critical issues. From the model, we can test to see if these influencing factors are indeed significant. So we're testing also that the design is robust against some of the real life things that will actually happen. So there's a variety of things that will affect this, and we need to be sure that these are covered. We have to also be sure that we're not getting caught into too much detail. So we also really have to consider that we do genuinely take these into account if necessary, but don't necessarily put them in if they're just putting in unnecessary complication. So I'll just touch on a few of the packages and we'll have a little look at what we put on them. Again, we're not trying to sell software here, so these are non-package specific examples. There's numerous packages. There's some that we've used, and to be honest, the list goes on and on and on. There is many, many. Most of them are fairly similar in what they do. They certainly have different eases of use. There's a whole list that could go on. I've used most of those there. There's some I've seen and I don't use them, but I understand what's in them. So it's about capability. It's about understanding how to use them and how to operate them. There's one there that is another. Don't need to say which one, but what goes into it? So we have reliability data, we have spares data, resources data, repair time data, logistic delays, and so forth. And we put distributions in. Now, if we're talking about a background level of constant failure rate, we would have a mean and we might have a normal distribution, for example. If we want to put in more variability around repair time, for example, then we might have a mechanical repair to be conducted, and we might choose to put a log normal distribution on that. And what that means is the distribution is skewed. And as we've probably all found with mechanical work, there's an optimum time it gets done. If things go wrong, it always gets slower and slower. There's a point at which it can't get any easier or faster to do. So generally, what we'll see is a log normal distribution. So when this model is running, if we've got mechanical failures, on each of those successive runs, there will be some where this failure is occurring more early or more later in the life. This failure will be occurring around the mean, but on occasion it will be out to the side and you've got that job which has gone horribly, horribly wrong. And on some runs, you'll get the blue skies where everything works, everything falls into place. So really what the model is doing is it is pushing out all those different combinations and settling out at where it lands in an average, in a mean sense over many, many times. And we noted when we had a look at the different life cycles. We might do this 1,000 times, but more often than not, we'll run it 10,000 times. Relationships. The model, you can see there, graphically represents what is often referred to as a RBD. That's a reliability block diagram. It's a very fundamental part of reliability engineering. It shows the logical connection of components within a piece of equipment. It's not necessarily the schematic diagram of the equipment or what we see on process flow diagrams or engineering drawings. It's the functional components and their relationships. So we would replicate things that are in series, and we would replicate things that are in duty standby mode in parallel. We might have, for example, 2 pumps operating at 50% capacity, so both are required. We might have our 2 out of 3, 3 out of 4 scenario, or 1 out of 2. So we mentioned earlier in regard of the benefits, why we might be doing this. So for example, we might have a scenario where we want to see how or what the benefits are from running, say, 2 50% capacity pumps or generators, where both are in full operation, versus 1 out of 2, where the duty unit is 100%. So we've got one with a backup, one with no backup, but if one fails, you only lose half the volume. We sometimes see that this is done with maybe, it could be 2 electric units, or 1 electric unit and 1 turbine-driven unit, for example, gas compressors, all sorts of combinations that we would map out with the reliability block diagram, replicate the process configuration, and graphically show in the RBD within the package. And we model in here things like I mentioned, buffer capacity. How long can those equipment run whilst other equipment has failed because there is capacity within tanks, there's ullage space. What happens when one unit fails? How soon do you go over to the backup unit? Can we put a failure rate indeed on the switchover? What allowance should we have for the backup unit not starting and so forth? So these again are all of the variables that go in around the equipment and their relationships. So what do we get out the other end? Well, in our example here, it's given us total durations of a particular uptime. And from that, we'll get an availability, or if we were monitoring throughput, perhaps a production efficiency. Now, usually in these models, we can set to do these and get these results relative to the point we are in the model. So we could look at the availability of a particular equipment, and we can look at the availability of the whole process plant. And we can choose whether we consider scheduled maintenance in the form of an annual shutdown as being part and parcel of that. We can model in perhaps a loss of, it could be grid supply, so we could model in some very high level events at the top of the model to see what happens to the bigger picture, in the sense of the bigger picture, and then see our results at the individual equipment level, or indeed just maybe the fenced plant, the onshore plant, or the process we have offshore, or within the manufacturing, or whatever it might be. This is very applicable to any throughput process. So when we've done this, we get a simulation output, which is invariably our percentage availability. So when the program's finished, it's totaling up the time in all the different states. And then from that, we get availability results at the various levels, system, equipment system, and overall plant. And usually what's requested is the availability of the delivered product, what you're passing out of your process, what's onshore. We might call it the over the fence availability, what it's going out to the next. Could be another process, could be to distribution, could be going out to the grid network or something like that. And we can plot this out on a chart and we can see where that availability lands most of the time. And we usually see something that's fairly close to a sort of normal distribution there. But what we can recognize is that in all those parallel runs that we did, there are some which are going to be particularly poor, and there are some which are going to be particularly good. But in the main, on this example here, we're sitting around the 99%. And then we would offer that as the validation of the design or the process, and that would be the answer. But always with the proviso that it would sit between an upper and a lower limit. And we could look at that and we could look at that spread and we could say, yes, the design is fairly robust because we've got a narrow spread. If we get a very wide spread, it's telling us that there's quite a variability in potential outcomes, and that might be a hint that there's things in there that need to be looked at, and then we would start to drill down into the model and look at what are the primary contributors, what's causing that. Is it equipment? Is it the design? Is it some of the factors that we've included, like logistic delays? Have we got a wide variability on repair times or a wide variability on failure rates and so forth? So it gives us a lot of reasons to start digging around in the model and find out what's causing that. So again, what I would say is sometimes don't get too fixated on the decimal points on the answer. There's other things in there. This can be very useful early on just to give you a pointer in the right direction. Your design's not robust because you're getting a wide spread of potential results, or they're a dominating factor. So there's a lot of uses that can be made very early on before really defined information is available. So that's it, folks. Thank you for listening. We've cases we can do this in oil and gas. We've cases we can do this in mining, manufacturing, fast-moving consumer goods, pharmaceutics, chemicals, power utilities. It's applicable. For example, in power and utilities, we're talking about generative capacity, the ability to produce electricity into the grid. Some of the early modeling that I worked on before packages were so sophisticated as they are now were developed by the generating boards, the old electric generating boards in the UK, to really support and substantiate the grid supply network, the availability of generative capacity into the network. So anything where there's a continuous throughput, there are slightly different tools. They work basically the same for batch processes. We have to consider those a little bit differently. There are particular packages that deal with, say, LNG tanker deliveries, for example. But in the main, where we've got a process that is a throughput, we can apply the availability simulation modeling to any industry, to any process. So we're now open to some questions.
Thanks, Mike.
If anybody has some questions, thank you, Don.
Before we head off and ask if anyone's got any questions, I'll give some time for those of you who don't wish to voice your questions to write them. Does anyone have any comments just in general, or anything they'd like to add to maybe what they've seen already? You've perhaps come across RAM before, and maybe you've got similar experiences to what Mike has been discussing. Nope. Okay, if we move on to the questions then, I'll once again give some people opportunity to think of any questions if they have any. I have a quick question for you, Mike. So if you were to go back, if you will, to slide 6, that's possible. I know there's a little bit of a delay on the slides.
Yes. So tell me when to stop.
It's not moved yet for me.
Okay.
I think I'm on benefits there.
Okay. Let's go back
It's moving very, very slow.
Okay, I'll run you back to the, is it the life cycle you want?
I think so, yeah.
Yep, okay.
There, sorry, excuse me, I'm going to have to come close because I don't have glasses on. I'll maybe turn my thingy off. Yeah, so we've got quite a massive variety of different sort of tasks in there throughout the full life cycle, as you've shown there. Now, the one that we've concentrated on, is this what you would think was one of the most important areas to do the RAM study model, or do you think that it's probably quite equally important across all of these sectors? You know, is there sort of areas where you might not need to do RAM?
No, all, and it's something we do get asked fairly often. People perhaps just really in the early front end design stages, they're really just doing concepts. Mm-hmm. And they do ask a question very often, can we do a RAM study here? Can we do a modeling study? We don't have data. We haven't done equipment selections. Yes, indeed, it can. What I would say is, again, it's really for looking at the step changes. It can just really model the basic design concepts. It can be used to test the robustness of the design. So, for example, you may be looking to see whether you have, let's say, 2 or 3 compression trains. So as a part of your front end, you'd be looking at equipment selections. You'd be considering things like weight, the footprint on the platform. You'd be considering cost and so forth. A lot of factors, weight and footprint affect the structure and the size and the shape. So there's all things that are quite normal to be taken into account. But the suggestion is that we should put more emphasis on modeling those simple configuration optioneering discussions and looking for those step change. So you might wish to stay with the configuration and say, well, okay, what are the differences if we go between an HV drive or a gas turbine drive? If we go, instead of having, say, 2 units, let's go to 3 units, 4 units, 3 out of 4 and so forth. If you went, for example, for 2 50% units running the total time, then your driver would be much smaller, and that might have an impact on weight or the layout, but it could cost more than having one larger unit. So it's perfectly normal to take those into consideration. But what we would suggest is it's great to be doing some simplistic RAM modeling at that time, because you can use the RAM model to arbitrate between those different configurations and see if there is a step change in the availability, the process availability of the product when you make those changes, because usually the factors like cost and weight and so forth will be the main driving. But how do you distinguish between them if you've no other measure? So we would suggest that a RAM model is a really great way to do that, even if it's fairly simplistic and even if it's using generic data. It still gives you the opportunity to identify how robust the design is against failure, or how the availability does or doesn't make step changes with those changes. Okay.
Thank you. Sorry, excuse me. Thank you, Mike. That was quite a comprehensive answer. There has been some questions that have popped through as you've been answering that question for me. So I'll go to the first one. This might be a relatively quick one. So we've got Anu, who said, good presentation, but how widely is RAM used in the oil and gas industry, and are there any limitations in using it?
It's fairly widely used. In some cases, it's more taken up by others. From the example I just mentioned, it's increasingly common that people are embracing it early on in the design. It is run throughout the operations phase as well, and we do get asked from time to time to do a model quite late on. Increasingly, it's useful in the late life phase. I gave an example, it's an oil and gas example, but when we get to the end of the life, we have a lot more water to dispose of. What assumptions have we made about that early on in the life, about the equipment that's going to deal with that? It's often said that the late life oil and gas processing platforms are almost like wastewater processing platforms, because the volume of water is so high as compared to the oil that the throughput and the, if you like, the criticality of oil pumps is completely different from at the start when compared to, say, wastewater pumps. So we can model that and consider that, but it is a mixed take up from different operator companies, to be sure. Some people are quite keen to get involved and do this, and I would be very keen to see these sort of models coming off the shelf and being a sort of management tool that are used regularly when considering any modification, operation change. It could be different logistics supply chain contracts that have been let, perhaps a different way in which you're delivering crew by helicopter, something like that might have an impact. So again, all of these factors could be accounted for in a model and different scenarios looked at. So yeah, very keen to have a model being used as part of the sort of everyday management. Probably suggest you revisit the model every couple of years to make sure the data is fresh and the relationships are still remaining true.
Okay, thank you. Annie, hope that answers your question. We've also got Stephanie Ritchie again. So she's asked made a statement, I suppose, to begin with, which is quite true. With any analysis, the output is only as good as the data that you put in. So how important is it to ensure reliable failure data, and where does the information come from for a new facility design, for an example? She's also asking if is there a industry data available for, as an example again, certain types of pumps for very specific services. Is there a sort of almost a library for engineers that they're able to draw on?
Data, yeah, it is always a question, and it is a difficulty with modelling a new as to be designed, or particularly at the very early stages. We can use generic data. Obviously, most people have heard of a reader for offshore, and in fact, things like a reader and other generic sources are used in a variety of industries as well. I've certainly used a reader, and I've used all the different versions of a reader over the years. There is a little bit of a feeling at the moment that some of the most recent reader, that's the offshore reliability database, is not so accurate in that the population, there's not so many contributors these days, so we're not entirely sure perhaps that the data is entirely representative. You can always test the data with your design people and your engineering and operations people. So it could be purely pragmatic data. In the later life operating scenario, then yeah, we can access systems, we can access Maximo, SAP, any of the maintenance management systems, and develop reliability data to go in there. That might be repair times, it might be failure rates. What we do see though is quite often how a plant is operated, logistic delay times, for example. Real life things have a huge impact over, you could be 50, 100% out in your mean time to repair, 12 hours, 24 hours. But if it takes you 3 weeks to procure it, and indeed you do see in systems that often work orders are held for quite a long time, awaiting spares, waiting for spares delivery. So factors like that can make a huge difference So you can see in the model sometimes that improvements in failure rates and repair times have a certain impact, but making your support and supply chain really slick and supporting the front line has a huge impact. It is a difficult area, there's no doubt about it. And I mentioned earlier as well that if you are using generic data, you can, so long as you're consistent in the application of it, you can then use the model to test the different scenarios and simply look for the step changes between the different scenarios. I hope that answers the question.
Thank you, Mike. Stephanie, I hope that answers your question as well. We got another one from Ryan Broadhead, and he's asking, as the wind industry is picking up, are we seeing growth in RAM outside of operators using original equipment manufacturers? And if so, is wind-specific data available, such as from OREDA?
It's not as yet from a reader, and it is an area of interest for sure. If you imagine you've got a large array of wind turbines, perhaps one of the larger offshore ones. Now we know we see some of them not turning, and that is very often because there's literally no demand, so they're feathered out and just idling. But often you will see others, and you've got the different scenarios around the visits. We certainly have inspection requirements and maintenance requirements like anything else. And as with most offshore, it's not easily accessible. So a just-in-time maintenance or supply chain regimes perhaps not going to be suitable, and we can quantify that with a model. I would say that generally the wind farms are applicable for sure. I'm not sure off the top of my head whether any of them do into the grids have a percentage, if you like, this generative capacity. If they do, it would be within their contracts of supply. So that's a very good example of where, if there was some dispute as to what the design could do going forwards, we can always measure backwards. We can always look for what the delivered availability was by considering the records. But if we had a design and we wanted to be able to say, yes, we can fulfill our supply obligations, then certainly we could use a model for that, yes.
Okay, thank you, Mike. And Ryan, again, hope that answers your question. If anyone does have any other questions, please feel free to write them. I think we will only have time for the last couple of questions by Nitec. But if you do have any more, please pop them down and we can try and get back to you on those. So last few from Nitec then. He's asking, first of all, is Monte Carlo RAM modelling an iterative method? And is model validation required before using it for any about to go live asset or process? Validation
is certainly important. We would always test the water with the answer with an operator company. It's not an exact science, but it's always necessary. If you make the model too optimistic, and you're suggesting you're getting 99.999% availability of some process, then I suspect people might question that. So there is always this validation of, does that seem reasonable? Conversely, it could be too low. So in terms of developing the model, yes, there is a certain iterative to it that we would always go back to the operator. We would look at the main contributors to unavailability, question what are the drivers, and just test the water on that. Is that reasonable? And once a model has been validated and is felt to be reasonable and representative, whether it's for the early life work or later life where it's got a lot of real historical information in it, there is always this test. Very often that test is fairly pragmatic because the operator company might say, well, actually, the reason we're doing this is because we don't have an accurate value of what the process availability is. We may have some uptimes. We may have things from the process and control systems and things like this. And we've got to judge it against that and decide. Once it's deemed to be valid, then, as we mentioned before, we can start to look, we could involve it in things like management of change, that when a change is going through or a module is being added or a new tie-in or some other change to the plant working scenarios or configurations, or even just the way in which the plant is managed, that we can replicate that and then we can trust the answer. So there is a little bit of testing the validity with the operator who has the experience and the judgment, if you like, to say, well, okay, yes, that does. And once that's done and accepted, then you can start to use it for the different scenarios.
Okay, thank you. Nitec does have a secondary question, and what he wants to know is, can component failure dependency be modelled, or can only single component failures be considered?
We can do our models at any level we like. We can do them at the component level. Obviously, you couldn't really model a whole platform, offshore platform or refinery at the individual component level. It would be unrealistically vast. So the advantage, one advantage of doing the package route using different software packages is it's fairly easy to drill down. So we might represent something at a fairly high level, run the various scenarios, and if we don't need to go into deeper levels of information for that particular element, fine, leave it. If there's things we want to explore, we can simply drill down to another layer. So what's represented as one equipment is obviously made up of lots of subsystems, so we can drill in and then populate the subsystems, and then from the subsystems we can go in and populate down to the component level, but as required. And if we've got data, if we've got, for example, if we've got a lot of items that are effectively in series, then you know, at the component level, then do we really need to model those in an RBD component by component? Because what we can do, if they're all in series and it's purely in series, then we can aggregate the data and have an equipment level element within our model. So it really depends on what we're doing with it and the need and the question, do we really need to go that deep? There's no point in going to increase levels of detail if there's no useful purpose from it. So we need to always be aware of where we're going. Always keep an eye on the answer. Why are we doing this? What are we using the model for? Do we really need to go to that level? Because we don't want to make a burden on ourselves to have data, populated data elements that we're going to be forever chasing, when actually a slightly more coarser number would have sufficed.
Okay, thank you. We've got one last one. So this is from Barry. I think we've got enough time before we wrap up. So he says, excellent presentation, Mike. Established industries with maintenance strategies that have not changed for decades will find it difficult to see the benefits, or rather the value in spending money and resources on RAM. From your experience, how open are such industries to using RAM for the first time?
Yeah, it can vary enormously. There are some industries which see it as a nice to have, and there are some which see it very much as an integral part of the process right from the early stage. So it's certainly true to say there's a fair mixture. We had a look at the benefits. There are benefits, there's tangible benefits that can be described. So we would always play to the benefits, and there are benefits. And for some industries that have never really done this, it can be difficult to convince them. But one of the aspects is that they don't really know where they stand, and they don't really know what their process availability is, other than just operational records. So one of the additional advantages to say, well, look, we can model this. We will give you a tool that enables you to understand what is going on within the plant, what are the drivers, what are the contributors to unavailability, and really ask the question, do you actually know where you are now? And that is something that potentially is appealing to somebody that hasn't engaged in this, to get that perspective.
Thank you, Mike. I have, that's actually one question I would I've got some input on, and I'd say that I am, to an extent, in my limited experience, I would also agree, very much a mixed bag, and depends on oftentimes the person that you're speaking to as well, not just necessarily the company or industry that you're talking to. But that is us coming quite neatly up to the hour mark. Just before we head off, I don't know, Rod, Mike, if anyone else has any other comments that they would like to offer. If not, then I think we'd be good to wrap up in a few minutes' time.
I'd just like to say thank you very much for joining us. Some good participation, good questions, well answered, Mike.
Thank you.
Didn't need me to jump in and do it, but if Mike can go to the very last slide on the package there, it shows you our contact details. So if you have any other questions, you think of any questions as you move along and think through the afternoon, just drop us an email, give us a call if you think something we can help you with, or just get in touch.
Yeah,
great to hear from you.
That's all. Perfect. Thank you, Rob. And if there's not anything else from anyone, the recording will be sent out via whichever email you use to register for the webinar. So you will have access to it at a later date, and you will be able to revisit any of the aspects that we've covered during the webinar as well. We will be running a series of webinars over the year, covering various different topics. So while contact details are still up, if there's particular interest areas that you have, particular topics that you'd like us to do something similar with, let us know, because we'd like to keep it as relevant as possible, and to what you're doing right now. Okay, but I think that's come up to the hour mark. Thank you very much for everyone who has joined and participated, and we'll hopefully see you again on the next webinar.
Thank you very much.
Thanks, guys.
Thanks all.
Thank you.